Okay, there we go. Cool. Another week, another Rust Club. So last time we had a look at how Winnow works in general. Paul, I don't think you were there. Were you there? Did I just forget about you?
I was there.
Okay, cool. In that case, everyone here there? You were
I
okay.
was neck deep in the website. Yeah.
Right. There was someone who I knew wasn't there. Um, so I'll do like a super quick recap of how Winnow works if you have any context at all for what any of this library does, and then we can go through it. Um, so yeah, so Winnow is a library for parsing, and it lets you define really, really simple parsers, like match a single like a character, a single lowercase a character, or match any character from lowercase a to lowercase z. And then it also has combinators, which let you combine smaller parsers to make bigger parsers. Like there's an or combinator. So you can have one parser that parses A to Z, lowercase, one parser that parses 0 to 9 character, and one parser that parses capital A to capital Z. And then you can OR those together with the OR combinator to make a parser that parses alphanumeric characters. And then you build those up into being larger parsers. So here's an example. We have, yeah, cool. So bless you. We have a parser called operator. And this is going to parse out a KCL operator. So alt, short for alternate, is the OR combinator that I mentioned. So we're matching any of these literals, matching like comparison operators, like greater than, less than, equal to, or kind of control flow operators, like the pipe, arithmetic operators. So these are all these are all like really simple parsers. And then we're combining them together with the alt combinator to make a more complicated parser. The type signature for Winnow parsers, you always have an input. You can call the input actually just input, but because I type it out so often, my convention for Winnow parsers is the input is always called I. So if you're using Winnow, I does not mean index into an array, it means input. So the input is a string reference, and it's wrapped inside this new type called located. And that's interesting. We haven't seen that before. That's actually a Winnow type. And if we mouse over it, it says allows collecting the span of a parse token. Spans are a range of byte offsets. So located wraps up some other input type, and it keeps track of the byte offsets into the original input type. And this lets you collect the location within the input. So the other part of the type signature is, of course, the return type. So we see we're getting this PResult, which is short for parser result. And it's parameterized by the output type, which is a token. So token is a KCL type that Kurt and Jess made. So we see a token. Every token has a token type. Token type is an enum with all these different kinds of tokens you can have, kinds of grammars. Things like numbers and words, but also kind of grammatical things like a period or two periods, and even comments. So we have a token type, and then we have the start and the end range within the source code. So this way, when we're tokenizing, we can always tell where does this token actually correspond to in the user's input. And this is really useful because now when you have an error, when you have like an unexpected token, we can return to the front end the exact place within the source code this token is located, which means you can highlight it really easily. This way, if you have like a long comment or something, and you now like mouse over the comment, you can see, okay, I know what token that is, I know where it starts and ends, so I can make it glow or highlight or anything. So you have the start offset, the end offset, and the token value itself, which is just a string. Any questions about how the KCL tokens work? Yeah.
Yeah, you showed us the located type, the like wrapper type. Would that also that seems byte offsets seem like the same as what our token.
Yeah, exactly. So the located new type wraps around the source code that the user is providing us, and then we use that to get the values of start and end for each token.
Okay.
So this takes in as input the located span, and the output is a token. And we see that when we run one of these parsers, like alt, it gives us back two things. It gives you the value, like what was parsed out. So in this case, if we put in greater than or equal to, the value will be greater than or equal to. And it also gives you the range within the source code that it corresponds to.
Yep.
So we call this parser and we add .with span. That gives you the span of the output from start to finish, start to end. And then parse next, we put in the input and we get out the output. That actually runs the parser. And then we get out the token value and the range. And we have this token from range function, which just takes in the range from Winnow, unpacks it into the start and the end, and then we supply the other fields, value and token type.
Nice.
Yeah.
Other question I have was and if this is too in the weeds, that's cool. But there's a R followed by a double quote. Back, I always get the direction on slashes wrong, but that R
This
tag.
thing?
Yeah, what is that?
So that is a raw string in Rust.
Oh, okay.
R just means raw string, so like don't interpret some characters as being like escape codes.
Got it. Okay, great. That's a way of you wouldn't be able to use that character just in your code if you hadn't tagged that with the R.
Yeah, so really, but the other thing is that the hash sign, that is saying treat quotation marks as quotation literals. It's basically saying, hey, most strings are delimited by like a double quote symbol. This string is delimited by slash quote and then hash quote and then quote hash at the end. So it changes the delimiters for a Rust string. And you can see that at the end, we're using also, the same little reverse thing here.
So that you can use double quotes.
Exactly. We can use double quotes inside here, and we don't have to escape them or anything because we've just used a different kind of delimiter for the outside of the string.
That is so cool.
It's really useful, especially putting like inline JSON into Rust strings. Yeah. So we had a look at so obviously there's really simple parsers, like getting a single comma, right? Again, we're going to assign we're going to declare two variables, value and range, and they come from using this really straightforward comma parser. And we use .with span to tell when I don't just want the parser, I want to parse and get the like span output, because Window's not going to do that unless you ask for it. So we tell we want the span, and then actually run the parser. So .parse next tries to parse whatever you wanted from the start of the input. And if so, it kind of consumes that part of the input and moves the cursor of the input along to the next part. So this is why the type signature here takes a mutable reference to a kind of window over a string. So when you run the parser, if it succeeds, it's going to mutate this window by moving it along, like by kind of consuming all the characters it needed to. So in this case, it's only going to consume one character, the comma character. But in this case, it could consume 2 characters here. So let's see how we actually use this straightforward comma parser. Yeah, we don't, because this is all the tokenizer, right? So the goal of this part is we take in, a source code stream of just a big string of KCL, and we convert it into being a list of tokens. Every token, we know what type of token it is, whether it's an operator or a word or a literal, and we know where in the source code it corresponds to. And by doing the tokenizing upfront, which is also called lexing, by doing that stuff upfront, we then make the parser itself much more straightforward, because the parser can now take in a stream of tokens. It doesn't have to take in a stream of like characters from source code and have to worry about tracking the offsets and all that kind of stuff. Yeah, so these are all, this is how we find the various kind of token features of KCL. And the only really complicated part here that I want to show you is dispatch. So to talk about dispatch, let's first real quick go back to, okay, actually, before we get there, let's take a couple of little intermediate steps. So I've got this inner word parser, and that's used in the word parser. So the inner word parser is looking for one of either lowercase letters or uppercase letters or underscores. It gets one of those, and then it gets to repeat 0 or more. The same thing, but now it can contain numbers as well. So we treat the first character cannot have numbers, and then we parse optional like 0 or more other characters that can have numbers. So notice that this parser returns like unit, bracket, bracket. So that's a bit weird. Why is it not returning the value that was there? So the inner word, this is just going to, all it really does is if it's successful, it's going to mutate the slice. It's going to advance the slice along for every character that it consumed. And it's going to return basically okay or error. And that's helpful because we can just make that its own little parser, and then we can call it from here. There's the .recognize method. Produce the consumed input as a produced value. So it's going to say whatever the inner word part matched over, that's going to be the new output instead. So this way we don't have to keep track of all the different characters. I could have made this say, let first char equal that, and let following chars equal that, and then do format something like this, right? But the downside to that is that's going to do a lot of allocation, right? I need to like store a vec of characters here, and then I need to join them all into being a new string over here. And that's, totally fine, but it's going to be faster to just use this one to kind of count. Really, it's just counting the offset within the original slice. And then this is saying, okay, now that you know where the token starts and ends, just take all of that and put it up into its own new token. So this is actually something I didn't really appreciate about Winnow when I started, but then I was talking to someone from Cloudflare a few years ago, asked me how to do this, and I was like, oh, just get the first character and then get all the rest of the characters. He's like, yeah, but then like how do I do that fast? And I was like, oh, yeah, that would be a little slow if you were doing something like super performant. But I don't usually do that kind of thing. It's like, well, this is running on every single like packet that I receive because I'm writing like a firewall with this. And I was like, okay, cool. So it actually does, allocations actually do really matter in this particular context. Fair enough.
That's sweet.
Yeah. Anyway, so recognize is a I think it's kind of simpler than having to join up your own string, and it's also faster. So what's not to love? But yeah, anyway, when you do a really big alt like this, it just has to try every single alternative until it gets to one that works, or if none of them work, it fails out. So you can imagine this could be a bit slow, right? If you have a lot of different parsers in them. All of these parsers are really quick because you're just literally checking the first character. That's either going to work, or it's going to fail, or you're going to have to look at the second character to make up your mind. So these are all pretty quick, but if you had a more complicated parser, it could become really slow because what if the last one matches and you have to try all these unsuccessful parsers first? So you can imagine, okay, well, maybe I'm going to do something maybe I'm going to try and run the most likely parsers first. Like I'm going to think about my language, which ones are the most common. I'm going to run those earlier, like on the left part here, and use my really rare ones on the right instead. But you don't know ahead of time, maybe which one's going to be more common than which other ones. So that's why we have this dispatch macro. It works really similarly to a match statement in Rust. So we're going to run this parser here first. And this parser is peak. So peak wraps around another parser, and it says run it, but don't actually consume the input. Just like peek at the input, let me know what you find there, but don't actually consume anything. Don't actually mutate the window. So we peek at the first character, the first token, the first character to come out, and then we can use that to choose which parser we do next. So you can think of this as being like an alt, where you get to run just a little bit, and then you get to choose which alt branch to run after that. So for example, if the input starts with a double quote or a single quote, I just like based on the grammar of how KCL works, it has to be a string token, right? Brace start, a parser matches these three tokens. So, if you peek and you see one of those tokens, it has to be that parser that you're trying to run. So on with this one, obviously, a comma or a colon or a period are all pretty obvious. Periods are interesting because you can actually start a number, like just 0.9. So in that case, we can have narrowed it down to a choice of 3 possible parsers. And so on, so forth. If you start with a /, you'll be starting a kind of comment, or it could be the divisible, like the division operator. So yeah, dispatch makes it is like a speed optimization, basically, to make it faster to know which one you're trying to do. Any questions so far? Cool. Okay. The other nice thing about dispatch is it makes error handling nicer. Because with alt, let's take a quick look at what this parser result type actually is.
Oh, wait, 1 second. Is dispatch a macro?
Yes.
Oh, okay, cool.
Yeah, that's why it's got the little exclamation mark here.
I'm gonna have to wrap my head around that. That's cool.
What's weird about that?
It's you are providing, you're calling peak within that macro, and then you just have, it looks like a very long sort of return statement because there's no semicolon at the end would be like default fallback.
Well,
But
there's
there's what?
This line here is the default.
Yeah, all the way down there. So all of this, the match arms,
yeah,
are a returned statement. Is that a tuple? Are you returning like a?
It's basically saying like, run this parser here, and then match the output of that parser against every left-hand side. And if it matches the left-hand side, run the right-hand side parser.
Right,
So
but this isn't a real match, right?
Sorry?
This isn't a real match though, right? This is like a...
Well, let's actually expand this and see what the macro is doing. So the macro actually is just a match.
Oh, okay.
We don't really, you could write your own match statement here, but it's kind of, they've provided this macro for you.
Yeah, okay, great. So do you need the peak any statement if it's, oh yeah, that's only expanded because you included it the first time.
Exactly.
Okay.
It's including, the specifics of what I put in there.
Yeah,
We
okay.
can look at the definition of dispatch instead, and we can see what it's doing here. So, it's taking in some expression, and then this is macro syntax for like a list of stuff. So it's then taking in a list of patterns, and then maybe a predicate, and then expression. So yeah, you can kind of see. Yeah.
So
I don't
you
actually
included
understand how macros work. Like I couldn't tell you like what the specific syntax is, but if you kind of like squint at it, you can kind of get the vibe of what it's doing. It's like a
I
very
get the
like
vibe.
it's like a poetry.
It's E. Cummings writes Rust.
Yeah, it's like I'm like purely looking at this visually, and I'm like, oh yeah, I can kind of like glaze over the bits I can understand and see what
Impressionistic Rust code.
it's actually doing. Yeah. Yeah.
That makes
So
sense.
real quick, I want to just take a look at what PResult actually is. Okay, so it's a new type for just standard Rust result. Cool. And the OK branch is O, which is generic. O is like output type. And it could be an error as well. Okay, it's generic over error, but it gives you a default. So this is the Winnow default error type called context error. But it's wrapped in this error mode. And error mode is an enum. So the enum has three cases, right? This is for streaming parsers, where you don't have the entire input yet. You're kind of waiting for it on the network. So if you return this error, it's saying, okay, like get more input and then return to me. There's the backtrack, which is saying like you tried the wrong branch, basically. In a big alt statement somewhere, you tried the wrong branch, and so backtrack, go back up, and try it again. Or maybe in like a like something like repeat 0 to n times. It's saying, okay, you've passed like 13 items, and you tried a 14th, and there wasn't 14th. So backtrack, and there's only 13 of them now. And this one is called cut. Cut is like, do not backtrack. This is invalid. So, for example, say you're parsing like a string, and it's going to be a string because it started with a double quote. So there's only one possible option it could be. And then there was like an illegal Unicode character. Okay, well, there's no point backtracking. The user's just done something invalid. You were in the right branch of the alt, but there's no like valid output here. Or if the user starts typing like 0.7 QQ, you were definitely parsing a number. There's no other KCL syntax that starts with 0 point something. But the user, has done something invalid, so there's no point backtracking. There's no point trying a different branch. Just cut your losses and leave. Any questions so far? Cool. Okay, so this is the tokenizer. We're just parsing 0, one more tokens. And we call this .parse method. Notice that parse is different to parse next. We're not doing parse next here. Parse next says like, hey, try and get the next token from the input, and then just mutate the input window. You've consumed something from it. Parse says you have to finish the entire input in this one go. So parse is going to make sure that by the time you finish these tokens, there should be nothing left in the input. And we can see that it returns this result. We get a vector of tokens, or we get a parse error. And the parse error contains the remaining input left over. So you can see what that way you can show the users a better error. Cool. Any questions about the tokenizer?
The Winnow is using those two other error types, those two first ones that aren't cut internally, whenever it's doing its like dispatch and parse next?
It's using all three error types internally.
Okay.
Yeah.
Okay.
In this case, so there are many different kinds of input type you could give to Winnow, many different input streams. This one, which is just like a string, that that implies like you've got the entire text there, right? So they're never going to return the incomplete error because you already have the entire string of memory. You're trying to parse the entire thing. There's no point where you're like, hey, I need to buffer and get more data. But if we're using a different input type, like like a network connection of string or something like that, then it could return incomplete and wait, like return that back up, and then some outer loop would get more data and then call it.
Okay, cool. So all three of those error types are coming out on that.
Yeah, exactly. Yeah. Cool. And I have like very you can see that this file, like the first 150 lines are the parser, and then the remaining 1,500 lines are the tests, because my tests are like very verbose here. Like I've taken in sample programs and then just like compared them to the previous tokenizer, token by token, and made sure the output is the exact same. But then I deleted the old tokenizer, and I was like, okay, well now I don't have any tests left. So I'm gonna like make sure they're correct, make sure the two tokenizers match up, and then print the output, and then copy the output into the test. And now I have a test that'll always work. Yeah, cool. Okay. And so you can kind of see, you can see the token structure here. Like this input program opens with an empty line, which you see here. And that goes from position 0 to position 1. And it's a new line. And then the next thing we have is a comment, which goes for 20 characters long. And it has the value of the comment. And then we have another new line. And then the keyword const. So yeah, I think it's useful to have a look at like, okay, this program, like what tokens does this actually correspond to? Cool. I'm going to move on to the parser, unless there's any other questions about the tokenizer. Okay, cool. So parser. So this is a work in progress. I can parse most of KCL. There are some little rough edges that I haven't smoothed out yet. So firstly, I just want to quickly talk about how I'm testing this. I've got some specific tests, like here's a program. Firstly, I'm going to tokenize it. So use the tokenizer that we just saw before in the previous file. And then I'm going to run one of my parsers, like this parser to parse a function expression. And I'm just going to make sure that it succeeds. I'm not going to like interrogate what details the function expression are. I'm just making sure it succeeds correctly. There are other ones where I'm actually checking the values. So here's another test program. See, it's got a whole bunch of comments. So again, I tokenize it, and I pass those tokens into a parser called function expression. And then that expression, I'm going to, we can take a look at the AST types. Function expression. It's got a start and an end. It's got a list of parameters that it takes in, and it's got a body. So in this function expression, I'm going to say, okay, give me the first, if it starts with a comment, and then give me any remaining comments, like comment 0 and comment 1. And then I'm checking, okay, what was the starting comment? What was the first and the second comment? So we could also, we could add another check here saying like, that the expression should have no parameters. Run test. Oh, is this font like legible font size? Cool.
You could probably bop it one more up
Bop
for
it.
bop it up just for like if we publish the video.
Yeah. Okay. And then the other kind of test I have this big testing function here called check pauses work the same. And this is probably going to go away before like I merge the PR, but for now it's very helpful. So I just have a long list of different statements and functions of different programs, really, specifically programs. So const x equals negative leg2 plus thickness. And then for each test program, I tokenize it and I check what the original parser does. That's my expected output. And then I run the new parser, and that's the actual output. And firstly, I'm going to make sure that it actually does parse successfully. Otherwise, I'm going to terminate the test by panicking. And then I check, okay, they should really be doing the same thing. So this lets me make sure that my new parser behaves exactly like the old parser. In a perfect world, I wouldn't need any tests besides this, except doing this has actually revealed a couple of rough edges in the original parser. And so sometimes it's like, okay, well, yeah, they're not the exact same, but actually I think my new one's better. So that's why I've got other kinds of tests besides just this one. Okay, let's take a look at how the parsers actually work then. So, yeah, actually, yeah, that's a bit complicated here. Let's look at the arguments actually, yeah. So this is a list of arguments that get parsed into a function. So there's this value parser, which is parses some KCL value. We can see the result type is value. And if we look at the types defined here, okay, we've got literals. You can pass in a variable identifier. You could pass in an expression like 1 + 1 or fx or, f piped into g, piped into h. Or you could pass in an array or an object or f.name or -4. So we get 0 or more values, which are separated by this comma sep function. And what does comma sep do? It runs two parsers. It runs the comma parser, and then it also runs the whitespace parser, but that is wrapped in the opt combinator, which is short for optional. So you apply a parser, and if it doesn't work, just return none. Now, when you run a parser, you can add this context to it that says why you're running the parser. And this is useful at the end for error messages. So if the parsers don't succeed, you get this chain of errors that are built up slowly and slowly. So over here, we can see that we're kind of starting down. We run the comma parser. And then we run, optionally, the whitespace parser. And if it doesn't succeed, we post what we were looking for at the time. And then we actually run the parser, and if it's okay, I don't care about the return type. I don't need to put the comma anywhere. I don't need to know if there was a white space after the comma. So I'm just going to return unit. And that's being run from within this arguments parser. So we start looking for a value. And if we find one, we check for a comma separator, and then we run another value. If we find one, we look for a comma separator, and then we check for another value, and so on and so forth. And we collect them all up into being a vector. And if we look at the docs for separated 0, it says accumulate the output of parser separated with this sep parser. So run this parser separated, interleaved with this. And it only keeps the result of the first parser. So this is a really complicated type signature, but the examples, I think, make this much more clear. So they're running ABC parser separated by a pipe. And you can see here, when you run the parser with ABC, pipe, ABC, pipe, ABC, pipe, it returns the remaining input, which is nothing. It's consumed everything. And then a vector of 3 ABCs. Okay. If you parse in ABC 1 to 3 ABC, it's going to get one ABC out of there, but it couldn't find the next the separated parser. So it stops. It found one. One is more than 0, so it's totally fine. And this is the remaining input. And here, okay, we parsed ABC and we parsed the separator, but there was nothing else. So just give me the first token that you parsed successfully. Okay. Any questions so far about the parser? Okay.
That's crazy. That's really nice.
Crazy?
I just really like it. I like the context. Oh, does context get used in any situation other than an error?
No.
Cool.
No. It's only used if you find an error. If you never find an error, then it just gets this, it's never even run. Or yeah, I think it's like tracked, but then it doesn't actually output anything.
Okay.
Yeah. Okay. And you can see that if you look at the result type, PResult. If it's okay, you just get the value that you parameterized it with. So like vec value. And you see here the E equals error context error. And we get that little wrapper. Anyway. So I'm actually doing something different here, but we're going to get into that soon. I've actually made my own error types for this to track things, but we'll get there. So I want to show you a larger parser. Let's take a look at function expression. So we start a function here. I put a comment here so you know what it's actually trying to do. So it has a list of arguments and then a block with some code in it, and then the end block ends. So we parse the open parenthesis, and we pass a list of parameters and a close parenthesis. Now, then we can maybe be some white space. I'm going to ignore it. And then the big arrow here, and then probably more white space, and then open brace. And then there'll be a function body, and then there'll be a close brace. And we actually do care about the close brace to some degree, but we only really care about where it ends, because that's going to then become the end of this function expression here. So this ignore white space function, it's really just looking for 0 or more white space, and then I just, ignore if it fails. It's okay if it fails. I don't care if there's no white space there. It's not actually relevant to me. So that's why it's not kind of being assigned to anything. Any questions about how this one works? Cool. So now the parameters function is a little more complicated. So again, we have the separated 0, and we're looking for a comma separated list. But what I'm doing here is I'm looking for anything that isn't a closing parenthesis. So I'm saying grab 0 or more tokens that aren't closed parentheses, and they're separated by commas. And then afterwards, I'm going through all those tokens, which are possibly parameters, and I'm then making sure they actually are parameters. So I've got this identifier that try from token. And we can see what it's doing here. If the token was of the right type, then okay, it's an identifier. Otherwise, give an error. So once we've got that identifier, we then check if it is a valid binding name. What does that actually mean? Well, this is just checking to make sure that you're not going to shadow over something from the standard library. So you cannot declare a parameter called like line 2, because we don't have shadowing yet in the standard in the language. And so for now, it's going to say you cannot redefine the line 2 function. And then we're going to check, okay, was that, collect them into a result, like go through that list and make sure that they were all okay. And if there was an error, then we're going to map it to error mode cut, because we know we are parsing a list of parameters. There's no point backtracking. If you're in like a big alt block, there's no point being like, okay, it wasn't a list of parameters, go down to the next thing, because we parsed the opening parenthesis and we know we're declaring a function expression. So there's no point retrying, just avoid parsing at that point. Any questions about this? Okay. Let's take a little closer look at what the type signature is. So I is token slice. That is not a Winnow type. That is a type I declared. It is a slice. It is a slice, like a window into an array of token. And we saw the token type before. That's the KCL token type. So what this is saying is this is like a sliding window over a vec of tokens. So the vector of tokens has a lifetime, but because we're referencing it, we're not taking ownership of it. We're just iterating over it. So that has a lifetime, which I've called input because it's the lifetime of the input. And then the window itself, it also has a lifetime. This lifetime is called slice because you can mutate the slice. The array is never going to change, but the boundaries of the array of the window are going to change. We're going to slowly parse tokens out, and then we need to backtrack. Okay, go back to where we were before, and then try parsing them again. So we need to keep track of the lifetime of the array, because if you drop the array, the parsers will be parsing invalid input. So this is saying the parsers have to live for at least like less time than the overall input does. And then we're also saying the window itself, you cannot run the parser if the window itself goes away. So any questions about this input type we've defined here? Cool. I think more people should communicate lifetimes by like doing this and that and crab hands.
Gantt chart.
Yeah.
Crab Gantt chart.
Yeah, exactly. And so I want to talk briefly about error handling here. There's this PResult type, but this is not the PResult type that you saw before. This is not from the Winnow standard library. I've actually defined my own PResult type here. It's very, very similar. In fact, my PResult is like a more specific version of the Winnow PResult type. So again, you can choose whatever O for output type you want. Like maybe you'll be returning a parser with a program. Here O is program, or a parser for like a comment block, which is called a non-code node, or a parser with a pipe expression. Right? This is the O type. And error is a reference to my mod error, module context error. So why did I do that? Why specify the error type here? Because we don't want to return general Winnow errors. I want to return the KCL error type we've already defined. Right? That's the type that the front end is looking for. So I want my parser to guarantee it's returning the same type that the front end is looking for if there's an error. So let's take a look at this context error I've defined. I've got this module error, and we're using its context error type. So error will accumulate context while it's trying different parsers. And if it needs to backtrack, it'll keep that context in mind. So the Winnow context error type, that can keep track of an error, but it's always like Dyn standard error. How do I put that more clearly? Winnow's errors by default are Winnow's errors by default have this cause field. But cause, you can see, is anything that impulse standard error. And we want to be more specific. We don't want to just let any, any error be the cause. We want to guarantee there's always a specific KCL error that causes the parser to fail. So my errors, they can have a cause, which is a KCL error. It's not option, dyn, standard error. It's option, KCL error. And they can accumulate context. Context is generic, but if you don't choose a value, it'll just be the normal Winnow context. And over here, I'm saying you can make a KCL error from a Winnow parser error. Winnow parser errors give you the input, which is the list of tokens you try and parse, and the output, which in this case is a context error, right? Because the whole reason we're doing this is something went wrong. So, firstly, let's check. Was there anything in the input? What was the last token? If there's no last token, that implies the whole file was empty. Well, there's your error right there. The file was empty. Then otherwise, check what was the offset at which it found the error. If the offset of the error is longer than there were actually tokens, that's saying, okay, we couldn't find enough tokens. Like you were trying to parse 3 tokens and there were only 2 tokens left. So the file was ended unexpectedly. So KCL errors always have a source range, and that's what we kind of highlight with a little red underline in the front end. So, you know, I'm saying, okay, just put a little like, we'll say that the source range for this is just the last token. And that way, at least the user will be looking at the end of the file and be like, oh yeah, I didn't end the file. This is actually arguably a bug, or we decided it was actually a weirdly documented feature of Winnow. Because I assumed that the offset of the error would always be a valid like index into the input array, but it's not if there's like not enough data left. So I opened an issue on Winnow and I was like, hey, this, you know, like if I only have 10 tokens and it reaches the EOF unexpectedly, then it says the error is with token 11, but there's no token 11. So it now is documented more clearly that you should check this, not blindly index into the array. So if we check both those cases, we know there is a specific bad token that caused the error, like an unexpected token somewhere. So yeah, we put that in. We then get the inner context error from it, and we can then check what the cause was. If there was a KCL error as the cause, we use that. Otherwise, okay, we'll just say that there's an unexpected token, and we'll show the user where the token happened to be. And in the future, we can be smarter about this. In the future, we can say something like, look at the context that we built up. And we can say, if the user is trying to parse like a function expression, and the most recent error is could not find an open parenthesis, then we should say, it looks like you're trying to write a function, but functions have to start with a list of parameters, and list parameters goes between parentheses like this. So there's definitely room to improve these in the future. But for now, the errors are okay. And then this is implementing a bunch of different traits that Winnow needs us to have so that we can use our own custom error types with all the Winnow machinery. So yeah, Winnow needs to know when you call .context in the parser, what should it actually do? Well, just put it onto the context array that I've got, for example. Any questions about all this stuff? Cool. I was pretty impressed by how, by the fact that I could like straightforwardly kind of rip out all their error handling stuff and replace it with KCL errors. That's kind of the strength of using generics here, is they've provided all these generics and they have defaults for them, but you can override the generics and choose whatever you want. And as long as you implement all the right traits, you can use all the nice kind of Winnow ergonomics that you want.
Yeah, that implementing from is like beautiful there.
So here's an example of where those errors cause come from. So if I'm trying to parse a Boolean value, I'm going to get any token, and then there's this try map expression here. So I'm going to take the token, and I'm going to map it to something, and if it's okay, the parser succeeds, and if it's error, the parser fails. So match the token type. If it's a keyword and the value is true, then okay, then you know what the value was. This is just how the existing parser works. It treats true and false as keywords, and then the parser interprets them as values. So, and anything else, return a KCL error. So this KCL error is going to be put into the cause field here. And then the overall parser that runs at the very top will get that error back out. And it'll get an error with the right source range for the token that was weird, and a message saying why it was weird. And then we put some context, what we're expecting. And if it works out, we put the start and the end range, and we get the bool value out. You see this try map a lot because the built-in Winnow things we use in the tokenizer, Winnow comes equipped with a bunch of primitive parsers you can use for parsing out characters for a string, or a sequence of characters from a string. But when you're using your own kind of custom token type, and you're parsing a slice of your own custom tokens, Winnow obviously has no functions to deal with KCL tokens. So instead, they just have functions to deal with generic tokens from some array, like any. Get the first item from the array. And then once you've got that item, you can then choose what to do with it with try map. So the map takes in a token, and if it succeeds, it returns a KCL value type. No, it returns Serde. See what it's doing. Okay, it is actually returning a JSON value, because that's how we track like literal types like strings and numbers. KCL is piggybacking off JSON types for its literals, which maybe will change in the future, because I don't know if JSON's number handling is exactly how we should be handling numbers. We might want to distinguish between integers and floats in the future, but for now it's totally fine. So yeah, we're trying a couple of different things, and there's error cases. Like if you try to pass in like not a number, that is a valid JSON value number, but it is not a valid KCL token. So we will not allow that. What are some other things you can do? There's verify. Verify is a lot like try map, but it just the closure output's a bool. So it's kind of like filtering, right? You take any token, and then you verify that that token matches operator. The token type is operator, and that the value is an equal sign. And if not, then instead of returning a KCL error, the parser just kind of fails. And so that's why cause here is an option. Because if I use .verify, there's no KCL error to be seen here. All we get is the context. So arguably, maybe I should change it to being a KCL error, but I feel like the context already explains everything. It's like you're looking for an equal sign, you found something else. It'll be clear what that something else was, because Winnow kind of keeps track of the error at which it stopped, the token at which it stopped. So yeah, arrays. Okay, you parse an open bracket, you ignore some white space, and then you get a list of elements, maybe some white space, and then you close the array with a closed bracket. And so, there's kind of this pattern of do some straightforward stuff, and then do some complicated stuff for the inner elements, which become their own smaller parsers, and then we do, the closing stuff. So in this case, the inner elements can either be like 0.10, or it can be 1, 2, 3, 4. So I look for one of those two things. One of those two kinds of things can appear within an array expression. And if neither of them appear, then we error out. yeah. Any questions? Cool. Okay. Well, this is how the new parser works.
This is really helpful. It's awesome.
Oh, thank you.
Yes, we didn't answer the question. What's been the hardest part of
Oh yeah.
writing this?
The hardest part is that there's just so many little details. Like there's so many little differences. Like the hardest part has definitely been comments, I think. Like just comments are hard to do because generally programming languages ignore comments, right? Generally, when you do the AST, you ignore all the comments. But because we want to refactor the user's code, we need to be able to preserve their comments. We actually care about where their comments are because if we say do some code generation, like the user draws a new triangle in the visual editor, we don't want to just erase all their comments because we've then like reinterpreted their code. So we have to match and preserve their comments. And not just that, we want to match and preserve the comment formatting. So there's this whole concept in KCL of like, well, in the KCL like compiler tooling of a non-code node. So it has a start and an end like everything else does. And it could be one of four things. It could be comment like this, like 1 + 1, and then have a little comment on the same line. Or, got these block comments here. Or it could be a block comment that has like an empty line above it like this. Because we want to make sure that the user's like spacing is preserved. If they've put a paragraph break, keep that. And then paragraph breaks as well that just don't have a comment below them. So because we want to preserve all these things, I can't just use nice little neat combinators like separated by with a new line there, because I actually need to know how many new lines there were. So as a result, the comment parser is pretty complicated. I keep like finding new edge cases and then adding them in here. And I figure that, that's okay because at some point I will go back and be like, okay, now that I've got all the edge cases accounted for, now I can like step back and think, okay, can I refactor this in a more elegant way? So, within the non-code node, I've got a non-code node that has leading whitespace and a non-code node that has no leading whitespace. And then I'm just running either of them. And this is a pretty common pattern you'll see. Like, I'm like, okay, there's 3 different ways this could go. So I'm going to define smaller functions for each of those ways and then just OR them together. But, this is kind of complicated, right? I look for a non-code node and I check, okay, if it was a white space, then I only actually care about it if it was an empty line. Otherwise, it's just random white space. I don't need to preserve that. I don't care if it's like 3 or 4 spaces between 2 words. I only care about it if it's like an empty line and the user needs to like keep in their program. And then tracking these is complicated. If you take a look at like the pipe expression, pro tip for any code base, just do like Control F and search for sorry, and you'll find like the good docs, So parsing a function body is complicated because a function body is like a series of assignments that are separated by new lines. You cannot have, KCL does not have semicolons. It actually might be much simpler if we did have semicolons, but we don't. So they're separated by new lines. But new lines can't just be ignored because in KCL, new lines are semantically important for comments. You need to preserve how many new lines there are, and you need to check. So I can't just use the separated one parser anymore. I have to like specifically check. Sorry, let me take a step back. The things within a function could be either a body item, like a declaration or an expression or a return statement, or they could be a non-code element, like a comment or an empty line. And so I'm looking for a series of either of these two things, like they're either expressions or they're comments on new lines, but they're separated by new lines. So you don't want to like consume like a semantically relevant new line, be like, okay, that's item number 4, is there's an empty line here. And then be like, okay, but there's no new line now. So the function is invalid. It's like not got a proper separator. It's like, no, that was the separator. You just parsed out the separator. So there's no built-in Winnow combinator for this because it's such a fucking weird use case to be like, generally you want to check it to be separated, but the separator can also be part of the main parser. And so don't reparse the separator a second time if you just consumed one from the second parser. So I just copied the Winnow like separated implementation here, which obviously uses a loop because it's doing something over and over again. And so I copied it and like changed it where I needed to be things be different. Like match over whether you found a white space and whether the last relevant section was an empty line. And then, look for the empty line as a separator, but if the previous thing you parsed was an empty line, then skip through it. So that's pretty ugly. But sometimes real-world languages are more complicated than the set of tools you get from the little parser library. So I now actually really appreciate why like things end in semicolons. It would have been much easier to parse if every like declaration or thing had to end in a semicolon. If KCL had like a concept of a statement and then ended in a semicolon, this would be much easier. And it's still an alpha. Maybe we'll add semicolons to simplify the parser, but
doesn't like the V8 and like JavaScript engines actually have, even though they allow like no semicolons at the end, it auto adds them before it parses the JavaScript, right?
Yeah.
Because that makes it easier.
Yeah, exactly. So maybe we'll do something like that in the future, but then we would need to track whether the semicolons were there or not.
Right.
Just like we would always insert them back into the source code afterwards for the user. But I kind of feel like if you're going to always require them anyway, then just make the user put them in the first place. But yeah, I don't know. And you asked me this is all talking about what the hardest part is. I think there was something else that was really hard, but I don't remember what it was. I think it's kind of like two sides of the same coin. Like this, like parsing function bodies is hard because of the non-code nodes, and the non-code nodes themselves are also hard to parse. Oh yeah, that's the other thing is because like I want to handle like inline comments. There are, you could either have every line of the function can either be a body item or it's a body item followed by a little inline comment. Like let x equals 3 / 3 is my favorite number. So then at the end, once you've parsed all these items, I do this big loop over like everything was found in the body. And I check, okay, was it an actual body item followed by maybe a comment? Or was it just a comment? And then I have to unpack. It's just like a lot of different options because language is quite flexible. We just unpack all the different possible ways it could be. And we loop over them and we reassemble the body at the end. And of course, we need to keep track of like the start and the end of the statements. We know how to highlight it properly. So every time you unpack something, it could be the first thing, so you need to track the start. And it could be the last thing, so you need to track the end. So yeah, it's ugly. And this is like the longest parser by far. This is what, how many lines? Like, yeah, like 130 lines. Whereas most of the parsers, as you've seen, they're like 1 line or like 3. So yeah.
Wow.
Yeah, any questions about that? Or
no, just really impressive.
this is why it's taken me 2 weeks to do this task. I kind of thought it would be simple and then thought it would be impossible, and then kind of found a middle ground of like, I'm just going to start with the parts I know how to do and slowly make my way through it. Oh, that's the other thing that I don't know how to do yet is right now the language is pretty simple around binary expressions. So right now we don't support saying like 1 plus f of x you have to say, let num equal f of x 1 plus num. And this is because if you try to do that at the moment, the parser becomes like infinitely recursive, because an expression can always be like an expression and then an operand and then another expression. And we do not yet have a way to make that like non-infinitely recursive. I know there are ways to do that, because clearly, you know, real world languages have solved this. So I'm sure there's some paper somewhere about how to do this, or there's like, you know, like an MIT lecture about compiler theory about how to do this, but I just haven't watched it yet. And I was like, damn, how did Kurt do this for the original one? I was like, okay, cool. He didn't. He also just was like, yeah, just like readable. And I'm like, okay, yeah, that's good. We'll ship like a useful language, and we will slowly, improve it. And I think we even give you good errors about this to explain why. Yeah.
That's a sorry.
So, you know, we even give like, okay, we found a value, but you cannot use that value in an operator because it would make it impossible. And we give them a link to the issue. So,
Wow, nice.
yeah. You know, the best programmers are always apologizing to their users. Let everyone know that I believe that. I'm very sorry to the users. Yeah. Well, that's it. Yeah, any other things or thoughts or comments? I know we've gone over time, so thank you for bearing with me. This has become like, you know, this is like a very therapeutically helpful session for me to kind of decompress over the last 2 weeks and stuff.
Rewiring your brain.
Yeah.
I think in the future I'd love to hear more about like, because I'm trying to get better about testing on the front end and writing unit tests for all my stuff. So like multi-file right now. And I know I've heard the word fuzzing used around, but the like how you think about testing the surface area of something, especially as complicated as this parser and Lexer, is interesting to me. And I'd love to hear like how that works, or how we find and improve tests over time. And
Yeah. So parsing like the test, this is actually like a dream to test, because it's just pure input, pure output. Like the input is a string and the output is a string. It's deterministic. You always get the same thing every time. So you can just build up like a nice table of tests, like you're writing a Go program. Like, you know, input, expected output.
oh, nice. Yeah.
And then, you know, you run those every time. You make sure you don't break anything. And then we have tests to make sure that the errors are good. Like, yeah, like, you know, if you put in, try to assign like a string to a function, then the error should give you the right source range, and it should say, you know, expected to find let variable, but I found a function variable instead. So we have errors for things that work. We have tests for things that work. We have tests for things that shouldn't work, that they you know, when they don't work, they return a good error or something. And we have a bunch of like just weird expressions that Jess and Josh found. Yeah, it's weird shit like this. And then, you know,
Those categories, that's helpful, honestly. Even just like if I can wrap my head around, like I need to make tests for the happy path, tests for a good outcome on the bad path. That's a good back.
yeah, and tests for just weird fucked up stuff to make sure
And then
like
a growing bucket of weird
something
fucked up
happens that doesn't crash. Like this, you know, this is like a shit error, right? The file is not empty, but it just fails to tokenize, but at least it doesn't crash or loop forever, you know? So yeah, we'll get to that stuff eventually. You know, I've tracked it in a little to do with a little error message, and And we also have fuzzing, which is just running random inputs through it and making sure that they at least terminate, making sure they don't crash and they don't loop forever. Noted in the Rust compiler test suite, there's a file called weird expressions, which is just weird shit that you wouldn't think would compile. But now that it compiles, we have to make sure it always compiles, otherwise it would break backwards compatibility. So I'll
That's good to
link
know.
that in the summary of this video. Cool. I don't want to take up any more of your time. If anyone has questions, just put them in the Rust Club chat after this. Cool. Thanks, y'all.
Thank you so much.
Yeah, hope this was helpful.